All right, let's jump right in. Today we're uh, really digging into some foundational stuff in math and set theory.
Yeah, ordered pairs and Cartesian products sounds maybe a bit formal, but they're everywhere.
Totally. And we're using the sources you've provided, so this deep dive is custom built,
Yeah.
really trying to get a clear, quick handle on these ideas.
Exactly. So, we often talk about sets, collections of things, like apple, orange. The order doesn't matter there.
Right. Apple orange is the same as orange apple.
Precisely. But sometimes the order is the whole point. And that's where ordered pairs come in.
Okay, so the sources define an ordered pair pretty simply. It's like a pair of objects, say A and B, written like AB.
Mm-hmm.
And the key is that the order matters. So AB is not the same as BA.
And plus, of course, A and B happen to be the same thing, like 3, 3, 3. But yeah, generally different. The first thing is the first component, the second is the second component.
And the sources give that great example. The set 6, 8 versus the ordered pair
Yeah.
6, 8.
Yes. That really nails the difference.
Because 6, 8 is exactly the same set as 8, 6. You swap them, no change.
But 6, 8, that's one specific thing. And 8, 6 is completely different. Think coordinates, like you said earlier.
Ah, right. Like on a graph,
Yeah.
go over 6, up 8. That's one spot.
And 8, 6 means go over 8, up 6. Different spot entirely. So that order is crucial information.
Makes total sense. And this ties into how we know if two ordered pairs are equal, right?
Absolutely. The material is crystal clear.
Right.
X, Y equals A, B, if and only if.
The first parts match up. So XA and the second parts match up, YB. Both have to be true.
Yep. No wiggle room. First equals first, second equals second. That strictness is what makes them reliable building blocks.
Okay, I think I've got a good handle on ordered pairs. Order is king.
Yeah.
So how does this lead into Cartesian products?
Right. So the Cartesian product, usually write it A, egg, B, kind of takes this ordered pair idea and applies it to whole sets.
Two sets, A and B.
Yeah. The definition in the sources says AB is the set containing all the possible ordered pairs you can make.
Where the first component, the first element in the pair, comes from set A.
Exactly. And the second component comes from set B.
So you're basically making every single possible combination, but keeping the order specific. A first, then B.
You got it. The sources have that nice simple example. Was it A, B, C, D, and BX?
Yeah, that sounds right. So AAB would be, let's see, pair B with X, then B with Y.
Mm-hmm. BX, B.
Then C with X, C with Y, so
Yeah.
CX, CY. And finally, D with X, D with Y.
Perfect. That's the set AAB, B, BX, B, CX, CY, DX, DY.
Okay. And then the sources also showed BEA, just to highlight the difference.
Right. So now the first component comes from B and the second from A.
So that would be XB, XC, XD, and then YB, YCY.
Exactly. And when you put those two sets, AAB and BEA, side by side.
They're clearly different sets. Unless A and B were identical or something, the pairs themselves are flipped.
Precisely. The order of the sets in the Cartesian product matters for the content of the resulting set of pairs. AB is generally not BEA.
But, and this was a really interesting point in the material, even though the sets are different,
Uh-huh.
the number of pairs in each set is the same.
Yes, that's a key property. The size or cardinality of AAB is just the number of elements in A times the number of elements in B.
So NAB equals NANB.
Right. And since, regular multiplication doesn't care about order, 3, 2 is the same as 2, 3.
Ah, so NANB is the same as NBA, which means NAEB must equal NBAA.
Exactly. They contain different pairs, but they always have the same number of pairs. They're equivalent sets in terms of size.
That's neat. It gives you a way to predict how many combinations you'll get.
Yeah, it's fundamental for accounting things, probability, computer science, lots of areas.
So wrapping this up from our sources then, the big takeaway seems to be understanding that critical difference. Sets don't care about order, ordered pairs do.
That's the heart of it. And that simple rule lets us build this structured thing, the Cartesian product, to map out all the ordered connections between two sets. And we even know how big that resulting collection will be.
It really makes you think, these aren't just abstract math concepts. You mentioned coordinates. I was thinking database records maybe. Input-output pairs in programming. Lots of applications. So maybe something for you listening to ponder. Where else does this idea pop up? This simple concept that order matters in a pair. Where does it bring structure or meaning to things you encounter every day?